Okay, I think we're ready to get started. First of all, I just want to thank everyone for coming out and pushing their dinner back and missing out on your deep racer time. We really appreciate it. My name is Mark Weiler. I am a solutions architect with the Global Life Sciences team here at AWS. And just a quick reminder, and I'm sure you've heard this 52 times already, but if you would please complete the survey after the session, we'd really appreciate it. And also to remind you that this will be recorded and posted on YouTube, so you can follow up later if you missed anything. So tonight we're going to talk about medical claims data, and every time you have an interaction with a healthcare provider, a claim's created. Now you can imagine that gets to be a pretty big data set pretty fast, right? And a company like Change Healthcare can process billions of claims, and this leads to a large data set. Well, this large data set also has a lot of relationships, right? Provider, demographic information, that sort of thing. And when you have a large data set like that with a lot of relationships, and that's a place that Amazon Neptune, fully managed graph database, really shines. So here tonight to talk about their intelligent healthcare data platform is John DeMastri, Senior Vice President, Platforms and Analytics at Change Healthcare. John?
Thanks, Mark. I appreciate that. Oh, more. So I know you guys have been busy today, but I do want to tell you one important thing. Magnus Carlsen won the World Chess Championship today in Rapids. So if you didn't know that, now you know. Now we can move on to some of this. So, as predicted. My name is John. I am responsible for a number of things at Change. One of them is actually the data platform that we'll be talking about, and a part of that, from an organizational point of view, will be the Neptune graph database, along with a number of other technologies that we're talking about here. But just a quick second or two on who we are. We're a really large, independent healthcare data service provider. We talk to 900,000 independent physicians. We have about 14 billion claims a year come through our systems at different times. We're, the independent part of this talk is really a unique space for us. I think there are other providers and other network providers that are either bound or working with closely with other stakeholders within the system. And I think being independent gives us a little bit of a distance that allows us to act a little bit more independently. So we cover everything from pharmacy claims to independent claims, or clinical claims to billing and other services. But one of the things I want to talk about is claims data, primarily today. And the key element here is the definition of what claim is. And the reality is it depends. There are many stakeholders in dealing with this process. And if you look at this cycle here, when you go and talk to your primary care physician, they may end up with a diagnosis, you may get referred to a specialist. At every point, when you touch some element of the healthcare system, there are claims information that get transmitted and sent. And every single one of these stakeholders looks at the data through their own individual lens. While the patient views this as, well, I have to have knee surgery, and they talk to 4 different specialists, and they have pharma associated with it as well, and maybe a month later there's audit detail that comes in through it. From each of those interactions is a specific transactional interaction that focuses primarily from the patient's view on getting well, and from the provider's view on getting well from the clinical point of view, but also getting paid to make sure that services are rendered for a reasonable value. And one of the things that allows us to be in a decent position to handle some of this information is about 2/3 of all the interactions that happen through the healthcare system today, we see at some point in the interaction. So about 70% or so of all the claims end up at some point through our world. And so, as I mentioned, there's a number of independent systems here, and handling at this scale is a very difficult task. And the 3 independent processes that we're showing here are typically things that would happen in series in a typical clinical incident. The first thing that happens is you may have an x-ray taken, and it would go through an imaging workflow. We have the technician that would actually take the x-ray. It would be sent then to someone to read it, and then the results would get sent back to your primary care physician. At a separate point then, the payment for that process would occur. The payments process would receive the claim, would go through the provider, and then an actual payment would get issued. And then at a third point later, when we're reviewing potentially the value for the care that was provided, or maybe we're looking over the overall value that a particular set of providers or a population might have, there would be an audit workflow that takes a bunch of claims in and then tries to come up with details around those things at a broader view. Each of those are independent workflows, but they work on the same underlying subset of data. And so there are a number of things downstream that constantly have to interact properly for this to work effectively. And that's one of the things that we're trying to build here to take care of that. These disjointed processes require specific data flows to work correctly. At every point where there's an interaction between the different systems, there are touch points where not only humans can frequently have to get involved, but also simple things that you would expect in normal large-scale processing data sets. Things like workflow IDs, claims processing IDs, the taxonomy around diagnosis codes and other things like that end up being unique to the underlying system. And I'm sure many of you all are aware of this. As you build large systems that interoperate together, we either have single sets of domains to rule them all, or we have disjointed domains that we need to have to find a subset that we can work against. And every one of those transition points allows for the potential of a mismatch or an error. As an example, if my X-ray technician doesn't put the middle initial in for my name, it may not match correctly to the payment, and that's a disjoint kick that has to be resolved by hand. So the system that we're describing here is intended to manage many of these interaction points, primarily by putting claims into commonalized forms, but also by taking care of the overlap and disjoint taxonomies, especially within identifiers. So the problems that we're trying to solve here are to improve overall transactional efficiency. As I said before, we have about a billion and change claims a month. It's about 13 billion claims a year that come through our system. Any small improvement in transactional efficiency gives us tremendous overall benefit to the system. We're also trying to get to systems where we have a common set of taxonomies and languages that allow different lines of business to be able to communicate effectively when they're talking about the same thing. As we're talking about many of these kinds of situations, as a payment provider, they may care about a small subset of the claims information, and they may care very greatly about the actual provider or payer that's getting the payment. But we want to be able to put the whole thing into context so that when we look at from the patient's point of view or from the payer's point of view, we have a consistent view of the information. And having the ability to do this more holistically allows us to shake out data and match and find claims and information, even where it's less relevant, or not less relevant, but less visible within the actual claims value, because we can match it to data that allows us to put it in context and get better view all around. And then the bottom line for large data sets is we can get better analytics out of the whole thing. So the method that we're using here is to take these transactional individual systems and place them into a much larger context that allows us to get a holistic view of this process. I have it hierarchically listed here from a patient's point of view, and typically that's the way we'll view many of these things, where we have patients and then clinical data that's associated with specific actions that's taken on behalf of the patient, and then perhaps payment data that's associated with the clinical data. But you can imagine the way this graph is drawn. You can take any of the objects here and shake it out to be able to get the clinical data view or the payment view, and be able to look back at the individual payment or patient view for a lot of this stuff. The actual transactional information is still tied back to the underlying data source, so we never lose the audit trail on many of these things, but it allows us to put it within a broader context that allows us to serve the specific stakeholders that we need holistic information about, whether it's the patient, the plan, or the provider. Integrating many of these systems together before we do final processing also allows us to get much more holistic benefits to both the provider and the payer, as well as just the patient. We get claims processing that happens significantly faster. We get better patient matching, which means less rework overall. But it also means that, importantly, we can get many of the manual steps out of the process completely and allow for these matching, payment, and transaction handling steps to be automated. So one of the advantages downstream is that we allow, with a model like this, to get application developers to be able to put systems into channel much more quickly. We have a common abstraction over many of these systems that reduces the number of stacks that we have independently. So there are Change Healthcare and the legacy systems that it was a part of are an amalgam of a number, just like many other large companies, it's an amalgam of a number of smaller companies, and each of them have their own way of doing lots of this work. By taking things like the network clearinghouse and putting a common abstraction over the top of it, allow us to take a number of clearinghouses, maybe half a dozen or more, depending on how you define them, and treat them as a single logical entity for handling, so that applications, analytics contexts, and other things that map data specifically across and between existing lines of business only have to talk to that one common engine and taxonomy. And it allows us to take many of the things that we do from a processing standpoint and remove the dependency on some of the things that happen in more of a real-time context. So when you think of a pharmacy context, when you're standing at the pharmacy and you've made the request for payment, they go out and check your eligibility in near real time. Obviously, putting data into a lake and processing at that point would not be able to handle those kinds of things efficiently. So what we try to do is separate the things that have real-time SLAs and requirements, especially the ones that are under a second, from the things that have much longer SLAs. And it allows each of those teams to focus on their core competencies, which has been a problem over time, where we have teams of developers that are responsible for some real-time things, some transactional things and some analytic cases, you end up with not necessarily the best of breed in any of those system designs. So how do we actually do some of this? The core of what we'll talk about for most of the rest of the talk is the Intelligent Healthcare Data Platform, which is our way of abstracting around the process flow and the information flow through our systems. And as you start to look at this, you'll see that we have kind of the 4 common sets of things that you would expect in many of lake processes. We have ingestion on the right, egress, packaging, and delivery on the left, and then lake storage in the center and a data processing tier in the right center. And Yi's actually in the audience, the guy that wrote this original diagram. I should have taken the watermark off, but it worked out okay. What I want to talk about here is each of these stacks in a little bit more detail and determine exactly why we picked both AWS as a partner to build this stack, but also why the process itself, I think, improves our overall delivery and time to market. It's important to note that we built most of the architecture before we decided what platform we were going to be working on. We had a number of relationships with cloud providers, and it ended up, after we looked at kind of how we built this, that AWS was the right fit for the majority of what we were trying to do, and they've been a great partner as long as we've been going down this road together. So from an ingestion point of view, we have a number of sources here that really need to be harmonized at rest. And what I want to be able to let you understand is the data platform is intended to capture all of the things that you'd expect to be able to capture on a platform like this. We have lots of data that comes across from a batch point of view where we get either FTP or other files. We have other systems that come in more interactively, as I mentioned before, like the pharmacy and other interactive models that come in with a SLA of kind of mid-real time. And then we have truly real-time operations where the network ingestion and operations have to happen in an SLA that precludes us from really doing all our formal normalization work before we put it at rest. And you can see the number of technologies that we have here that help us with this. We have S3, obviously, is our native storage element. Kinesis and Glue have been, Kinesis, I should say, has been using for the interactive and real-time work, Glue for transactional work, and then obviously the EC2 and gateway work for relevant pieces within this. So the goal for this acquisition and ingestion piece is to get data that's locally normalized. So at this point, we don't yet have the full universal identifiers normalized, but we're normalized to the point where the particular process that was pulling data has enough information to go ahead and do its work correctly. Excuse me for one sec. Just that work all by itself, just that work by itself goes a long way towards reducing a significant number of the mismatches and other things that happen in traditional processing, but it's still not quite enough for us to be able to put data at rest within our data platform for use across line of business purposes. And so that's really where the next 2 parts of this come into play. We call it a lake, but it's really the base core storage element for this. We maintain data at rest with reference to the original data source, and that's important because in healthcare, as I'm sure many of you are aware, the rights that you have to that data are very application and source specific. So we may have claims data from 3 or 4 sources that look identical from a structural and a semantic point of view, but the actual downstream usage may be very different depending on who's asking for the data and in what context. So we need to maintain that reference at source. We use Glue to manage transformation services, and here we're doing the final transformation into a more common taxonomy. Now, at this point, we're not imposing what I would call a traditional enterprise data model. One of the advantages that we have here is that we're trying to use data from a lot of different sources in a lot of different downstream contexts, including billing and other types of services. Imposing a single data model onto all of this data, onto billions of claims and similar numbers of payment data would be pretty futile. And I'm sure many of you have tried this in the past where you've tried to take a complex data environment and impose a single data schema on top of it, and the results have been less than exemplary. What we've tried to do here is we take data, catalog it to the type of data that we have, and impose internally what we've been calling a query taxonomy to be able to get the data out that everyone should be able to expect in a claims context or in a clinical context or an imaging context as an example, but yet still have the remainder of the attributes that may not be mapped to the core taxonomy so that an application can pull out all the information that it requires at execution time to be able to start to say, okay, I can see the 30 attributes that are the core part of the claim, but I need the typical attribute I always use as my random one is left-handedness. Let's say our machine learning team determines that left-handedness is an attribute that determines some propensity to a particular illness. Obviously, that's not a common part of a claim data, but we can ask for specific elements to be mapped to left-handedness, and that would come through as part of this dictionary or bucket of attributes that we would give back to the element. And we'll talk about that a little bit in packaging and delivery. It's important to note that we have a number of tools internally that allow us to access data rights appropriately, and some of the things that were launched this morning, we've been aware of for a little bit of time, and I think it's important that we use everything that resolves back to kind of IAM constructs typically. We're not building another identity tool on top of this that allows us to manage this. It's the appropriate way to manage internally at scale the data that we have here. And that the data is stored as Parquet. And the reason we're doing that is because one of the first questions I had from one of my developers was, hey, John, you're not going to have us build a brand new query engine for this, are you? And the answer obviously is no, that would be ridiculously inefficient. So as long as we get it translated down to Parquet, we can use pretty much off-the-shelf SQL and query tools to be able to get into the data. And so we use Ranger for cataloging, S3 for core lake storage, and Glue for transformation is the primary set of tools that we're using here. And I think when we started to put the architecture and design for this together, we had an architectural boot camp with Amazon just to make sure that we were doing everything reasonably. And I think the tool set that we ended up coming up with allows us to scale, but it also allows us to kind of be flexible in terms of how we deliver both data to specific clients, but also, as I've mentioned a couple times now, in the broader cross-application context. So the processing system is where we actually put the data at rest in capitals, like it really at rest. And we do three typical types of jobs to be able to make sure this happens. One is, here's where we do the actual normalization of raw data from the format that the application ended up wanting to the actual core query taxonomy piece that we share across line of business boundaries. The important thing here is that from this point on, anyone can ask for data and expect to see at least the core elements of it in a specific format that they can expect from any downstream usage. The second and third elements here are the pieces that really matter from the large-scale data transaction processing perspective. This is where we get rid of all of the local identifiers and replace them with global elements. This goes for patients, payers, providers, but it also goes to the things that end up making semantic context useful within the data, such as whether it ends up being diagnostic codes, any other global taxonomy that makes sense within a particular mode of kind of clinical delivery, or within imaging, they have their own sets of taxonomies that we're trying to provide common global identifiers for. The value here is that the data that we have, again, that isn't specific to a particular application is still retained so you can pull it out, but the things that should be normalized end up staying normalized. So the typical example would be that if I ask for a query of patients that have a specific diagnosis code and a specific time frame and a specific geolocation, we can ask that using the common query taxonomy pieces. But then again, as I said, if we have certain specific attributes for a subset of those claims, like left-handedness is a good example, they would still be returned back to the query and they would not go through this normalization step. The second part of that would be, though, that if I needed, for some reason, the original payer ID or the original ID for the plan for that individual, that would be returned back as part of the data set that comes in. So we have the data set in its normalized form, but I can always refer back to the original data that came in on the wire. I think that's an important part of this. Then the last part of this is that having that universal set of repositories for each of those scoping identifiers is a critical piece of that. So where we have typically a universal patient identifier or a universal payer identifier, these end up being core elements within the broader business and enterprise context. And the expectation would be that applications, as they come on board, make the explicit distinction to be able to start to say, I'm going to stop using my original local identifiers, and I'll start using the broader universal identifiers. That gives both the data that they add to the system, because this ends up being a round-trip exercise, much more value, because we end up with data that's augmented by a single application, and then it gets shared throughout the rest of the enterprise context, much more value. But it also gives, it puts a stake in the ground for how we want to use some of this data downstream. And it's important to note that although we put it at rest within S3 as a part of some of these Spark jobs, I think the structure and original scope of the data is kind of masked from most of the downstream clients and users. So we said on the last slide that it's a data lake in structure and in content, but it's not a traditional data lake in the sense that we just make it available for downstream users to query at random and to provide schema on demand. It's a part of the system's responsibility to provide schema on demand in the context of the query taxonomies that we've been talking about. And again, having the ability to do a lot of this stuff within AWS has been a tremendous advantage for us. So this is, it seems like a simple mirror image of ingestion, but I think there's a couple things here that I want to make sure we get to. So getting data out of a data lake is similar to getting data into the lake, but it's not quite, right? So since we're stored at Parquet, we're using traditional tools and SQL query mechanisms that allow us to get at the data much more quickly. But we have, again, a little bit of control around how we get data access off the platform more than we have when we bring it to the platform. So if you were to be able to provide access to your last 7 years of healthcare records, how would you go about it, and how would you deny access to it if you wanted to? Well, the query element here allows us to enforce data rights at rest for how we're allowed to use the data in cross-data contexts, both from a regulation like HIPAA and similar, but also from just a contractual standpoint as well. And we'll talk about that in a couple of minutes, and that's where some of the other interesting parts of this platform kind of come into play. And then from there on, once we have access to the right data, given the context that we have, all of the three main modalities that you'd expect to see from a data query and delivery mechanisms are in place. We have all the needs to deliver through batch, interactive, and real-time contexts. The difference here is that if we do a batch query for 17 million records or other large amounts of data, it's really critical to be able to page through that data in ways that your client expects to see. So we want to make sure that we have both APIs and other mechanisms semantically consistent across the entire data set, so that whether you're asking for payments or claims or other types of information, the semantics around how you handle data is consistent. And that's one of the mechanisms that the platform provides as well. And again, I just noted real-time in the sense that it's important to note that we want to make sure that things that are truly real-time get as little, a shorter path through the platform as we can make. And it's critical to be able to make sure that we get data that has true real-time contexts back out to those consumers as quickly as we can. And one of the ways that we do some of this ends up being through the way we handle organizational details. And here organizations end up being the physical providers or other folks that end up allowing us to talk about structure in those hierarchies a little bit more intelligently. One of the things that we have to do, and if you can look at the slide, Aetna as one of the examples here, and I apologize to folks in the audience that are Aetna folks, it's just written because it was originally Company A, and that was the Company A that I thought of. Aetna takes on two provider roles here in the sense that they actually ship us data, and it may not be their data, it may be their data plus other folks' sets of data. And they also appear as logical entities within the data that we get from them or from other folks. And in most systems, as I mentioned earlier, systems that are kind of siloed and distinct from each other from an enterprise point of view don't really care about that. They take Aetna, they put that at rest, and they don't really worry about the fact that, oh, by the way, there's some other use of Aetna that I have to be concerned about. Here, where I may have restrictions on being able to say, as an enterprise partner, Aetna may only want us to share data with these specific sets of companies or for these specific purposes. Understanding that Aetna as an embedded logical entity within data, and also knowing that Aetna is a provider of data that we may get for bulk loads of data or interactive feeds of data is a critical thing. And trying to resolve these two disparate elements is a core part of why we're using Neptune on the organizational side of it, and some of the folks are here that are involved in some of the identity pieces that we're working on, and we'll go through that in some detail. And then I want to talk about exactly why this is a useful thing for kind of providing better data, both from a quality perspective, but also from a performance point of view. So this is, we may refer back to this slide, but this is something I want you to keep in mind as we kind of walk through this context. So from an organizational point of view, if we're talking about things where we have maybe 100 sources of data and maybe 5 or 6 different use rights that we have to apply to, it's actually a pretty straightforward system to be able to employ a kind of a typical relational system on, to be able to do many of those joins. When we're talking about thousands and thousands and thousands of data sources, each of them may have maybe 50 or somewhere between 10 and 50 different contractual clauses determining how I can use their data outside of the original purpose of use, and then being able to tie them specifically to kind of the organization and role of an identity that we're getting from a third-party user coming into user applications. All of a sudden, resolving those joins at runtime ends up being a very computationally difficult problem. So if we're thinking about maybe 1,000 organizations, 1,000 different data sources representing them, and maybe 100 different applications, all of a sudden, for every single query, since we can defer rights across line of business boundaries, we may have to do 100 million different resolutions of data rights for every single row of data that we want to be able to feed back. And to be able to do that in traditional relational source, especially from the organizational point of view, just really isn't feasible. And I want to make sure that we talk a little bit about why. So we talk through some of this. I think most of the breaks that we're trying to do here, in each of the, like a traditional relational scheme, each of these verticals here ends up being kind of a join to a different set of tables. And while a couple of tables ends up being not a big deal for small numbers of data, in our case, there ends up being a little bit more of a problem to that. And one of the things I want to talk about here is our intent and our goal is to use Neptune to be able to resolve many of these things. Instead of starting at the organizational level or at the individual level, inferring the organization from the identity context, and being able to run through a rights table to determine all the rights that they have for every single table or data source in the query. What we're doing within our intelligent and access management system is taking a relational approach to this, where we can structure the organizational tree as a graph within Neptune. And what this allows us to do then is to take a single organization or an identity, map to their organization, and then we can see directly as a result of the graphing relationships that we have what the rights are that those individuals have. Excuse me, allergies are killing me today. And one of the things that Neptune has allowed us to do is to be able to start to build many of these things, and we'll talk a little bit more about some of that detail. But the key here is that we've sub-segmented the problem into determining exactly what data do I have rights to see based on the data source of who originally provided me that information at the start of the process. And we've decoupled that from the actual execution of the SQL query. By the time I get to the traditional SQL query, I've already have the identities of the data sets that I'm allowed to be able to make use of, so I can optimize the query appropriately downstream from that. So that's a little bit separate from this. So an initial query is just having, when we did our original bootcamp for this, we found that, that the original organizational query ended up being about an order of magnitude faster in this particular use than a relational query would have been at scale. And that's a little bit counterintuitive for many of the traditional complaints against graph systems. But I think one of the things we've been trying to do is be able to focus exactly what the relationships end up being, so that once we have an entity, we can quickly get down to the individual that we have. Let me just take a quick second and determine exactly what the hierarchy here that this is intending to represent. So if we take Aetna as the example again, at the root might be the home office, and then they may see the audit office along with a number of peers. And then within that, there may be a West Coast or an East Coast from the office. So the East Coast can see only their data. The audit office can see both East and West Coast of data. And then the root can see that. And actually, in many traditional relational systems, even this wouldn't be that difficult to model, because I have a root and I can make the dependencies pretty clear. It's this red box that throws in all the trouble. In many systems, we have the right to be able to say, hey, look, Aetna is deferring. The example would be Aetna is maybe based, and we'll make this up off the top, Aetna is based in Las Vegas, and they don't want to have any of their employees see any of their data. So they'll contract with a partner company to review all the claims that come in from Las Vegas. And so that partner company may also have relationships with a dozen other companies. So it isn't just a query that this company always has access to this particular subset of data. It depends wholly on the context of why they're asking for it, in what context, and from what application perspective. So quickly it becomes something where we have to iterate over the entire data set for every one of our data claims at query time. And so that's one of the reasons why choosing this operational model from an organizational point of view ends up being a little bit more of an elegant system. So at this point, I want to talk a little bit about kind of the workflow for both billing and other systems that we have within our context. And this is a simplified overview of what we have. And I think this model follows the architecture very directly, where we have ingestion, augmentation of the data, which ends up being both a locally internal piece where we have augmentation of data as a result of the processing that we're doing internally. But you should also think of that in terms of being able to provide like common methodologies and other augmentations of data that typical applications try to provide. I was talking to a group of developers earlier this year, and I basically said, well, if your data isn't augmenting, if your application isn't augmenting the data, why are you building it? And except for typical kind of reporting or other contexts like that, and even then you're providing value and augmentation for it. There's really never a good answer to that. So if you're augmenting data, why wouldn't you make that available through the platform for other folks to use? And so it ends up being kind of a little bit more of a cycle than the linear representation presented here. But if you think of augmentation as kind of the purpose for many of the processes that exist to add value, we'd want to make that data available downstream. Then clearly, within a single application context, query is a straightforward element. And here we're talking about query across line of business boundaries typically. So we have to make sure that between kind of Neptune, Ranger, and the other tools that we have in place, we can pull that data out of S3 and deliver it downstream to the clients within the packaging and returning elements of that workflow. So I want to give a couple of examples to show kind of how this is actually providing value for what we're trying to work on here. Within our payment integrity business, which is basically a fancy healthcare-based way of saying audit, we have a number of very specialized individuals that have skills in determining whether a particular clinical set of facts was either appropriately handled or not. And while there's a lot of work going on, including some of the work within kind of some of the SageMaker work that's been released recently by Amazon, to automate much of this stuff, and we'll talk about a machine learning example in a couple of minutes. The reality is that for the next couple of years anyway, probably for the near-term foreseeable future, these specialized humans are kind of the limit to how quickly this business can grow. And the example here is pretty interesting, because when I came on board to change healthcare about 2.5 years ago, this was one of my first projects to be able to start to work on. And it became clear that there was a number of hand-coded rules that have been put in place over the last 10 years or so. There were probably 100 man-years worth of efforts to maintain these rules over time. And at a pure just check of the usefulness of these utilities, one of the teams did an A/B test to see exactly what the value of those rules were. And the goal of this is to put high-value claims in the auditor's hands so they can turn around the highest dollar value per claim that they work. And so the rule selection mechanism is very critical in terms of making sure that they see the right elements. And the experts that have hand-coded the rules, so we're about as knowledgeable as we could be for this. It turned out that when we compared them with just chance rules, so if we had 1.5 million claims that we were going to pick one out of, or 1,000 out of, we would say, okay, a random chance of 1 in 10,000 goes through to the auditor's claim. And it ended up being that the 100 or so man-years of rules were actually no better than chance at resolving which one should be in the claim. So what we did was we simplified dramatically the amount of rule selection that we had. We made a much broader data set available for them to select from by having this data that was typically not available to them and putting it in the claims reference to be able to better select which claims got pulled into the optimization process. And then the first version of this actually ended up doubling the revenue on the same number of staff that we had. So being able to make broader sets of data available, transforming it and making it available to the application, it showed a very, very significant value without any real incremental cost to the business outside of establishing the system at this point. And again, the tools we primarily used for this were S3 at rest, Glue for transformation, and Ranger for cataloging and selection for a lot of this. Although I think the very first version of this was prior to us using Ranger. The machine learning example that we talked about here is it's kind of a meta example, and the next example we'll talk about this is similar in that it works across the process. Prior to having larger data sets available to deliver to machine learning teams, they had a twofold problem. One was to get data, and the other one was to make it usable within their data modeling context. So they typically would have to go to a number of my directs or our peers, maybe half a dozen or more, get a data set, and all of you are technologists. If someone says, hey, we're going to try to do something that has a lot of value, can I get data from you? The answer is going to be yes. So they pull that data in, figure out a way to normalize it, and then, oh, by the way, after the fact, they had to check to see whether they actually had right to use that data. And many times they'd have to go all the way back to the paper contracts, which is a problem for a lot of this stuff. So our CTO calls this turning scientists into plumbers, because it takes a group of very, very highly skilled individuals and makes them route data for a living, which is not something that we really ought to be having them do. Moving to a common platform allows us to be able to allow that team to effectively say, select start from claims within a given app context, have the data rights controlled appropriately, and have the data set returned to them already normalized and already in a usable format, so they can get their data model, they can get their model trained more accurately and more quickly than they would in the manual context. And so getting data to an operational form is much, much quicker, and we've already had significant advantages in order of months to be able to get data in terms of a shorter time flow for the earlier versions of our platform. So once we've gotten data into this, we've let the machine learning teams operate on it, the actual time to market ended up being about 3 months shorter than their typical model in production. So it's been very successful for us at this point. So the final example that we'll talk about here is about medical network integration. And we talked at some point earlier about how we've had a number of kind of logical abstractions over the disparate clearinghouses that exist within the world right now and in our system. Having common rules and configuration information that apply at that logical level allows both the details of the on-the-ground network teams to focus on the things they do best, which is the real-time network integration or operation, and it allows the upstream analytics and data management folks to work on the things that we do best. And the advantage here also is that it allows us to use the data platform as a single source of truth, rather than having to go through each of up to 8 different clearinghouses worth of operational data. It allows us to focus exactly where it belongs on some of the low latency transaction routing elements of the business, which is where, frankly, a lot of the overlap between those two pieces, between operations and transaction management and the low latency routing, has been a source of problems that follows us along from clearinghouse to clearinghouse. And most importantly, once we have the data in a common format, it allows us to have a single set of tools across all the clearinghouses. That means both operational at some point, and it also means all of the analytic and detailed elements that go along with having a single abstraction over the top of this. Let us put data into a much, much more consistent piece. So this is a big win both for the folks that have to run the network, the folks in my role that have to deal with the downstream data that comes out of the network, but it's also a big win for the business because they get much clearer view of analytics on top of all this information in a consistent form that allows us to add value much, much earlier in the process. I hand-waved just a little bit about data rights, and here we'll talk about how kind of Glue and Kinesis and Ranger as well kind of let us build a lot of this stuff. We've talked a little bit about kind of the platform that allows us to build a consistent view of data across operational traditional boundaries. And we've used both S3 to put it at rest and Glue to transform it into a common data form. I think one of the things that we've tried to be able to do is provide just enough structure and just enough schema to allow downstream applications to still use all the data in kind of as wide a set of application sets as they want to be able to use, but still have them come back across with a common access mechanism with a lot of this. And I think having this tool set that we're describing here allows us to really get to the bottom of that very, very quickly. Between having a common approach to how we store data at rest, a common approach to how data models are applied on top of the data at rest, and how access rights are enforced by both the system, but also the organizational structure that we've put together around this, allows us to have a consistent view of data in really any of the line of business contexts that we need to get data out. And then the forward-looking piece of this ends up being integration with other enterprise-level systems. So when we talked about the data rights slide, we talked about Aetna as being a customer and a data supplier, and also an element within the context of the supplied data. One of the things that we didn't really talk about is that data, or Aetna as kind of a true customer of ours, as a partner of ours, may have other restrictions in terms of how they provision users downstream. And one of the things that we're looking to do in very short order is to integrate this data platform with our enterprise systems to be able to allow a single source of truth across the entire enterprise for all of our partner level information as well. So right now, if we wanted to get, and again, we'll just talk about the context of it, if we wanted to get a use for how many Aetna employees had logged into one of our payment systems and pulled information across and tried to compare that to the contractual usage models that they had, it would have been, or right now it still will continue to be, a number of individual queries that have to be knitted together by hand, which is one of the reasons why we're building the system to begin with, to try to get out of that mechanism. So I would take away from this that we are an S3-based data lake, but it's not a formal data lake in the sense that we have data at rest that anyone can query and apply schema as they see fit. We're still applying quite a bit of schema on the output side to be able to provide a common semantic view across the enterprise for everything that we're making data available for. And then IHTTP with its data rights overlay allows us to get data out of the system and still enforce many of the contractual and data rights that we have, both from a regulatory and from a partner management perspective. And the way we do that is this is our little homage to kind of the platform within which the Intelligent Healthcare Data Platform lives. And I think one of the things we have is that at the bottom of this, we have the network that manages all the real-time I/O with external partners, especially for the interactive pieces that we were talking about. The Intelligent Healthcare Data Platform lives at this third tier, along with some of the DRM and other pieces that we've discussed. At the third tier and at the top tier is more of the client-side facing interactive pieces that we're building as well, because I think having a common approach to both data and UI is a critical piece as well. And I think having a common approach to how different application teams build software is enhanced by having this common approach to data and external services as well. The goal for us right now is to have about maybe half of our applications on board within the next fiscal year, and about 75% of the data that we talked about. And as I mentioned, it's about 13 billion transactions a year, the majority of that coming through the clinical network that we have. And so, runs out to about 10 or so billion claims coming through by the end of next fiscal year. And for now, I think we're well on track to be able to start to do a lot of that. Having the common approach, as we started to roll this out over the last 2 years with our development teams, we've had a pretty significant improvement in both application development team velocity and the throughput that they've been able to get, but also, even more importantly, the quality of the code that they've started to generate is really, really significant. And so, as we talked about it here, we have both the platform pieces at the top of this, or the platform UI pieces at the top of this, the development teams at the bottom of this, working on the platform and data rights management stuff. And I think this is something that will continue to allow us to make significant strains as we continue to draw this apart. I think one of the things that's allowed us to get as far as we have, as quickly as we have, has been having a great partner in AWS and a lot of the technologies that we've had come on board with this. And I think we'll continue to approach this as we go forward, as we continue to extend, especially the second tier here. Throughout the next year, we'll be starting to add kind of common business metrics and common logic on top of this that will bolt onto the data platform in a way that's kind of application neutral. And so that's kind of where I wanted to end with this. I think this, unfortunately, went about 10 minutes faster than we typically plan this because I'm speaking very quickly, and I apologize for that. But the advantage for you guys is that if you have questions or anything else, we can start to address those now, and we can either do that at the podium or you can reach out there and we can talk a little more further in depth about it. So thank you for your time. I appreciate that, and I look forward to answering any of the questions that you have. Everybody shy? Well, just come up if you have questions, and we'll talk about it in person. All right, thank you so much. Oh, please, go ahead. I see you now.
So this is a question about Neptune and the structure that you went with. Whether you went with Gremlin or Sparkle or EF, and what drove that decision? What is it? The type of data that you had, the sort of natural structure, the type of questions to ask of the data. What brought you down that path?
So for us, the real approach that took us away from relational was the way in which we needed to use data at kind of data rights management time. So it was specifically the relationships in the organizations that we had. So that's really the approach that we have. And I can get you more detail about the specific implementation work. But the real higher level problem that led us down that particular path was that just a relational structure would not have been as efficient.
Yes. My question is, once you've chosen a structure, you needed to choose between RDF and Apache Supercomp. So I'm wondering how you made that decision.
I have a couple of the architects here, and we can talk about that in more detail after this. Okay, all right.
You mentioned about controlling the access to data.
Yes.
Possible to do it at a field level or element level?
So kind of a traditionally row or column level access, right? So the traditional access rights that are implemented by the system are both row and column based at that point. There are lots of columns that end up being either PHI based or otherwise restricted from that point of view. So we have attributes that allow us to tag those elements in that way. Depending on the access, depending on either the restriction that's in place. So if it's restrictions in place from a regulatory perspective, we will limit that globally. If it's just from a single source restriction, we may have to filter it for individual records as we go through there. But it is possible to control both at the row and the column level. Basically, it's a cataloging tool to allow us to have a method by which we can access individual records or data sources, really, and control the rights access to those in that detail. So it's a way to catalog the lake that we have.
Is that something like AWS provided?
It's a part of the platform, but it's not an AWS-specific component. Oh, sorry.
What do you use for the interface to get data into the platform? Do you just take data from like any format, or do you use
Yeah, one of the operational issues that we had is that since we already have interfaces with thousands of sources, it would have been impractical for us to kind of impose some standard ingestion format and have that work. So we've tried to, and that was why the distinction between kind of the first and the second tiers in the architecture are so critical. We're trying to take data at rest in the form that we already get it from the provider and do that initial normalization to what we would consider to be a locally normal form. So it has to be semantically complete, but it doesn't necessarily subscribe to our final at-rest query taxonomy yet. And so between the first and the second pieces is where so in the first stage is where that first normalization would happen. So if one set of claims comes in as just some JSON object or JSON set of objects, and others comes in as just random CSV files, that first stage would put them into kind of a locally normal form that we can work downstream from. And then in the second stage, we would start to resolve both the differences between an application-specific schema and what we consider to be our formal schema at rest. Say again?
You use Glue to do that initial transformation for client?
Glue is involved both in that first stages, but not for all of the existing applications because many of those already have mechanisms that are in place. But once it's within our platform, that's pretty much the primary transformation mechanism that we use. Oh, I'm sorry, one.
So what are the query engines that you're using for interactive or batch? I mean, with that amount of data, what are you using? What kind of performance?
Well, again, it depends on Presto is a primary query engine that we're using to get into a lot of this data. And the performance of the actual data, the performance of the actual SQL engine isn't as much dependent on the engine itself. It's how we pre-select to get to the data that you're allowed to see. And then the formal data is a little bit easier to query through at that point. But we can, actually, a couple of the architects are sitting right behind you if you want to get into some performance details. So we can talk about that in more detail.
Looks like you mentioned how multiple different what we call payers are different types. Do you like a multi-tenant system or do you actually join the? Sounds like you also join the.
Well, the answer is yes in that sense. We're logically multi-tenant, right? But the point is that many of our clients have restrictions on how we control data internally, and we employ many of those schemes logically, right, within our data platform. So if our clients specifically ask us to kind of segregate their data, we're going to have a longer conversation about that. We prefer to have it within the same platform so that we can use it in a cross-client context. Now, many of the applications that we use for especially analytics purposes require kind of anonymization or other de-identification of data. And one of the things we do with pretty much all data that we have coming across is we have the raw version of it that are used in the local application context, and then we have a de-identified version that we end up using for a broader analytics context, and we use both of those within that space. I'm sorry? Well, in the sense that both, right? So in the initial form at rest on Lake, it's segregated, and then it's mastered for downstream analytics usage. So pretty much everything, if we cut everything off from the initial placement at Lake, you could consider it segregated. But I think mastering is an important part of the value of what we add for a lot of this data. Mm-hmm. Yes. Well, again, that depends upon the line of business, but one of the things that we are respectful of, and one of the reasons why the data rights application piece is so critical, is that for some use cases we really can't share data across line of business boundaries, and so we want to be able to make sure that that's respected. For other information that we are allowed to share, especially in aggregate form, we can share data across line of business boundaries, and that's actually one of the purposes for this data platform, is to be able to do exactly that purpose. We do have data products that we license that are sourced from this platform. We also use a significant amount of this data for internal analytics usage as well, and decision support and things like that, what you'd expect out of platforms like this. That's a really good question. The key services, I don't think we use key services. Yes, I'm getting the definitive answer of yes, that we are using key services from my architect over here. Any follow-up to that, or? Oh. Okay, cool. All right, thanks, folks. I appreciate your time. Thank you.